Hello.
Hello, can you confirm if I'm audible? Am I audible? Hello, am I audible? Uh, Hema, can you confirm if I'm audible? Okay, fine. So we can start with this week 11 live session for the course Digital Electronic Circuit. So I am Anand Singhal, a PhD student from IIT Jodhpur, and I'll be assisting in solving a similar week 11 assignment problems for the course Digital Electronic Circuits, which is taught by Professor Gautam Saab from IIT Kharagpur. And we have almost come to the end of this course now. In the initial 10 weeks, we have almost covered each and every sequential circuit and the combinational circuit. A moment. Okay, so in the initial 10 weeks, for the first 6 weeks, we covered all the combinational circuits. Then we started doing the important part of this course, that is the sequential part, and we covered all the flip-flops, resistors, counters, etc. And in the last week, we also covered some of the Mealy and Murray models that basically constitutes of the all the sequential circuits. And today we'll be solving some of the applications of this digital electronic force, which is digital to analog converters that are also known as DAC. Then there are several ADCs also, which are analog to digital converters. So we'll be seeing them also, and we'll be learning about some of the DACs such as weight, register, converter. Then we will be studying about binary ladder. Then accuracy and resolution will be solving for certain DACs. And in the next week, we'll be concluding this course with the memory topic. So let's start this week 11 with the first question. So this is the question: for a 3-bit weight DAC. So first of all, it is given it is a 3-bit weighted register DAC. So we need to find out the values of R0, R1, R2, and RL, which is given in the options. So one thing to notice here is R1 is 100 kilo ohm in all the options. So we'll assume that R1 is 100 kilo ohms because it is all the options are 100 kilo ohm. So I'll let you know the basic of this circuit: 3-bit weighted resistor DAC. So it is something like this. So wherever we apply the voltage, there are certain resistors which are associated to it. So let's say this is R0, then we have a R1, then we have a R2. So since this is a 3-bit, so that is why I'll only draw the three registers. So R1, R0, R1, R2, and at the last we have a load resistor which is grounded. So here we generally connect the MSB, the most significant bit, and the point where the voltage is connected, the first resistor is generally the least significant bit. So this is the LSB, and then what the relation is. So this is what we have. First of all, one thing to is RL is very high as compared to any of the resistor R0, R1, R2. That is, it is almost higher than three orders of R0, because this is the load resistance, so it needs to be higher. Then what we have is R0 is, let's say R0 is a resistor which is having a value of R0, then R1 is given by R0 by 2, then R2 is given by R1 by 2, that will lead to R0 by 4. So basically this is R0 by 1, this is R0 by 2, or we can write this as 2 raised to power 0, this is R0 by 2 raised to power 2. So for any n bit, we have a 2 raised to power n. So if I can try to write for Rn, so it will be Rn by 2 raised to power n, that is nothing but, again, you can write it as R0 by 2 raised to power n. So this is what we have for a uh, the description for a 3-bit weight tag. So this is for a n bit. So now we have already seen that the in the question, sorry, this is not R0, this is, sorry, this is not R1, but this is R0. So in the question, all the options are having R0 as 100 kilo ohms. And one thing here to notice is we need to find the RL also, which needs to be at least 3 orders higher than the R0. So this is 1 kilo ohm and this is 1 kilo ohm. So these options will directly get eliminated, and we only need to check from option B and option C. So let's say we have a R0 as 100 kilo ohms. That will give my R1 as R0 by 2. That will be 50 kilo ohms. Then my R2 as R0 by 4. That is 25 kilo ohms. So we'll check the options. So in option C, there is an inverse relation, that is, this is getting twice each and every time. So this is also wrong. So option B will be the correct answer. You can take a look. If you have any doubt, you can ask. We shall start the next problem in 1 minute. Is there any doubt in this problem? Shall we proceed? Okay, fine. So this is the next problem now. So in this problem, what we have is we have a R2R ladder DAC. So there are two types of DACs that we already covered. One is a binary weight DAC, then this is the R2R ladder. In this again, we have a combination of this 2R, R2R, R, something like that, and we have a input voltage, that is VA. The first bit is connected to the MSB, you can see here, and the last bit is connected to the LSB. And one thing to notice in this particular problem is this is the bits are getting converted to a binary to gray converter first, and then they are going to the input. So for the time being, we'll not think about this. So let's say this is a box, and let's say this is V0 dash, this is V1 dash, this is V2 dash, and this is V3 dash. So what we have in the question is the reference, the resistance is given as R, the V reference, the reference voltage is given as 10 volts. Then we have an analog output. So we have a V out of 9.37 volts. what is the binary input at V3 to V0. So we need to find out this, all the 4 bits. So first of all, we'll find out these 4 bits that are V0 dash, V1 dash, V2 dash, V3 dash, because these are directly related to the binary DAC, and then we'll convert them. So as you can see, this is a binary to gray. So if this is in binary, then it will be in gray. So to solve this question, we will get V0 dash, V1 dash, V2 dash, and V3 dash, that will be in gray, and we need to convert it to binary. So what we need to do is gray to binary conversion. I hope this part is clear what I have just said. Sorry. So now to solve V0 dash, V1 dash, V2 dash, and V3 dash, we'll just go with the formulas of the R2 ladder. So the resolution is given by V reference by 2 raised to the power n, where n is the number of bits. Then we have an input voltage, or the VA, which is given by this resolution times the input voltage, and here n is the number of bits. So we'll calculate. So n is given as I guess it is 4 bit, because 4 bits are connected. Then V reference I've already written, it is something 10 volts. So we'll calculate the resolution. It is 10 by 4. Sorry, not 4. This is 10 raised to 2 raised to 4, which will be 10 by 16. I'm not solving it. So we'll calculate the VA, which is 10 by 16 times V in. So since it is given the V out is 9.37, so we'll similarly calculate this by considering all the bits as 1. So this is 2 raised to power 3 into 1 plus 2 raised to power 2 into 1 plus 1 into 1, and last we have 2 raised to power 0 into 1. This will give me 10 by 16 times, so this will be 15. So this will be 75 by 8, and that will be 9.37. So which is also given as V out. So from this, what we can easily say that V0 dash, V1 dash, V2 dash, and V3 dash are all 1 1 1 1, because then only we are getting V out as 9.37. So but this is not the final answer, because there is a twist in this question, because we have a binary to gray converter. So for to find out V0, V1, V2, V3, which will be the final answer, we need to do this is, let's say, in gray, we need to do it in binary. So can someone quickly tell what will be the binary conversion of this and how to do it? So what will be the answer? Can you quickly tell? Anyone? Anyone know binary to gray or gray to binary conversion? So then I'll solve. So for to convert gray code into binary, we'll keep the first one same, and then do the XOR of the first come out one and the previous one. So 1 XOR 1 will be 0. Then this will get XORed with this, which will be 0 XOR 1 will be 1. And then this one will be getting XORed with this, which will be 0. So the final answer of V0, V1, V2, V3 will be 1 0 1 0, which is option A. So you can take a look at this problem, then we'll solve the next problem in 2 minutes. If you have any doubt, you can ask. So let's start the next problem now. Now what we have in the below circuit, there are certain values which is given. So we need to find the value of V naught if the input is this. So first of all, it is written that this circuit is a DAC 0808. So wherever you see a DAC 0808, I guess this is in your course outline. So this is nothing but a 8-bit DAC. And wherever you see this big circuit, there are only three values which you need to be careful of. That is the R reference, this is the V reference, and then this is R. So you need to see these three values to solve any of the problem that is given to you. So R reference is given as, I guess here, yeah. So this is 10 kilo ohms. V ref is given as 10 volts. Then we have finally R, which is given as 5 kilo ohms. So this can be solved using a certain relation which is given by this V naught is nothing but V ref by R ref. Then you can see there are certain bits. So A1 is the MSB and A8 is the LSB. So the first bit is the MSB. So this is how it starts by 4, then it will be by 8, and so on. And it goes to the 8th bit, that is A8, that will be divided by 2 raised power 8, and this whole will get multiplied by R. So this is the formula to solve any of the DAC 0808 question, which is nothing but a 8-bit DAC. So the formula is same as the previous case. It is just that 8-bit DAC is also called as this IC number, which is DAC 0808. So now to calculate V naught, we have V reference. V reference is given, which is 10 volts. Then we have R reference, which is 10 kilo ohms. Then we have these bits. So this is nothing but the input. So the input is given in the question as this is the input, which is 1, and the last bit is 1, and all of them are 0. So what I can write is 1 by 2 plus 0 by 2, sorry, but plus 0 by 4 plus 0 by 8, and so on. All of them will be 0, and the last bit will be 1 times R, which is 5 kilo ohms. So this kilo and kilo will get cancelled. So V naught will be, so 10 and 10 will get cancelled. 1 by 2 plus 1 by 256 times 5, which will be nothing but this will be 256 28. So this will be 129 times 5 into 256. And then if I'm solving, we'll get, so 2 point. So this is coming out to be 2.519, which is option D. Is there any doubt in this problem? So this is just a straightforward problem. So most of the problem in this lecture will be straightforward, maybe based on the formulas and all. You just need to learn these formulas, and each and every question will get solved in minutes. So just be aware of that. So if this problem is clear, you can take 5 minutes and let me know the answer to this problem. So this is again a similar problem. You need to solve the V naught if the input is this. So what one answer is C. So let's just calculate again using the straightforward formula. So again we have all the values given, which are Vref, Rf and R. So Vref is given as 10 volts, then Rf is 5 kilo ohms, and this R is 5 kilo ohms again. So I'll just apply the formula. So the output will be Vref by Rf, and then again A1 by 2 plus A2 by 4 and so on. A 8 by 256 times R. So keeping all the values, this is 10 by 5 kilo. Now we need to see the input. What is input? So the first three bits are 1 and all of them are 0 then. So it will be 1 by 2 plus 1 by 4 plus 1 by 8, and all of them will be 0. So I'm not writing the further bits, and R is again 5 kilo. So these both will get cancelled. So this will be 10 times 8, and this will be 4 plus 3 plus 1. This is 7. So the answer will be 70 by 8 for the output, which is 8, 64, 60. So the answer will be 8.75. It is option C. I hope it is clear. You can take a look at it, and then we'll be solving the next problem in 2 minutes. Let's move forward if it is clear. Now again, this is a question. It is given that this is a 16-bit DAC having a full scale range. So this is known as FSR or VFSR of 0 to 8 volts. That is 8 volts as a full scale range. If the input to the DAC, so V in is given as DEC16, then we need to calculate the output. So first of all, we need to convert this input into the decimal equivalent, and the output will be nothing but the resolution, which is the full scale range divided by 2 raised per n minus 1 times the input. This is how we can calculate the output of this particular question. So for that, we need to convert this V in into decimal value. So can someone quickly do it and let me know what will be the decimal equivalent to this? So this will be, so in hexadecimals, we have A, B, C, D, E, F, which is 10, 11, 12, 13, 14, and 15. So D will be 13 times 16 raised by 2 plus E will be 14 times 16, and finally we have C, which is 12. So this will come out to be 256 times 13 is 3328. 14 times 16 is 256. 224, and this is 12. So finally what I'm getting 842. So finally is 4, there is 6, there is 5, 3. Can someone confirm if all they are also getting the same? So this will be in decimal. Yeah. So it is 3564. So the final output will be calculated by BFSR, which is given as 8 volts. Then we have 2 raised power n. So this is a 16-bit DAC. So we need to write 2 raised power 16 minus 1 times V in. So this is 8 by 2 raised power 16 is 65536. So it will be 65535 times V in. So you can use your calculator to solve the same. Let me know the answer. I'll also calculate. So I'm getting 0.435. Is there any option? Yeah. So option C is the correct answer. I hope it is clear. You can take a look again, and then we'll proceed to the next problem in 2 minutes. Is there any problem in this particular question? I hope there is no problem, so we can proceed further. Okay, so this is again a simple question, basic. So it is given that it is a flash type. So the questions that we were doing before were digital to analog converter, but this is a analog to digital converter, which is also known as. So this is one of the converter which is flash type ADC. So it is asking which among the following figures denotes the relationship between the number of bits n. So this is number of bits which is in the x-axis and the number of comparators required. So flash bit ADC is a circuit which requires certain comparators. So let's say these are number of comparators which I'm denoting by, let's say, Fn. So there are Fn versus n plots given and we need to check what is the correct answer. So first of all, for the number of comparators that are required for a flash type bit ADC are 2 raised power n minus 1. So you need to remember this. For a flash bit ADC, for any n bit flash type ADC, you require 2 raised power n minus 1 comparators. So this, first of all, this cannot be the answer because this is constant. for each and every n. So this cannot be the answer. So option C is eliminated. Then we have 2 raised power n minus 1. So for n equals to 1, we will have 2 raised power 1 minus 1, that is 1. Then for n equals to 2, we have 3. So 1 is correct, then 3 is also correct. Here for n equals to 3, we have 2 raised power 3 minus 1, that will be 7, which is not correct here. This is 5. So figure 2 will also is also wrong. So since this is a very small labeled figure, so we will assume that this is correct, and we can check for 6. So for n equals to 6, we have 2 raised power 6 minus 1, which will be 63, and that is around the same 63. So this is correct. And for n equals to 8, we have 2 raised power 8 minus 1, that will be 255, which is also similar. So figure 1 is the correct answer. So this will also be wrong, this will also be wrong. So option A is the correct answer. Is it clear? This was a simple straightforward question. You just need to be aware that for any flash bit ADC, the number of comparators required are 2 raised power n minus 1 for n, which is the number of bits. Is it fine with everyone? So let's move forward then. So this is a important question, so be attentive here. So again, this is a ADC question, which is a SAR ADC question. SAR ADC is nothing but successive approximation register type ADC, which is one of the most important ADCs that we generally cover in any of the ADC and DACs. Uh, so we have a 8-bit type, 8-bit SAR ADC, which is given in the question, which is used to convert 4.75 to digital output. So this is the input which is getting converted to digital output. The reference voltage is given as 12 volts. So the question is the output at the of the ADC at the end of. So end is a very important word here. End means after the third clock pulse, after the start of conversion is. So we have a SAR ADC. So we have certain relations. So V reference is given here. 8 bit is also given. So N is 8. Then V in is 4.75. So what we need to calculate? We need to calculate the output after or at the end of third clock. So what we'll do is we'll first of all see for the 0th clock. So I am hoping that this is also already covered in the theoretical lecture. For the 0th clock pulse, we know that for the SAR ADC we start with all the zeros. So we will have 8 zeros, 5, 6, 7, 8, which is less than mean. So we have a concept that if the SAR ADC is less than mean, then we remain the bit, and if it is greater than mean, then one gets converted to 0. So I'll let you know what this is. So just be with me. So for the first clock cycle, so what happens is this first bit becomes 1, and then the rest of bit becomes 0, 6, 7. And if the decimal equivalent of this is greater than that of V in, then this 1 is getting discarded and it changes to 0. And if not equals to, if less than V in, then this 1 remains 1. So now what we'll keep this. So what we can write is if VDAC is greater than V in, then discard the 1. If VDAC is less than V in, then you can say this is reset and this is keep the bit. So we'll just apply these things. So what we need to do to calculate if VDAC is not, so first of all we need to calculate the resolution again. Resolution is Vref by 2 raised power n minus 1. Vref is given as 10 in the question. Sorry, it is 10. Oh, it is 12. And it is how many bits? 8 bits. 2 raised power 8 minus 1. So this is 12 times 256 minus 1, and this will be 12 by 255, which is 0.047 volts. So we'll calculate for the first clock pulse, the decimal equivalent will be, the V out will be, so this is 0, 1, 2, 3, 4, 5, 6, 7. So 2 raised power 7, because the 1 is only present there, times the resolution. This is 2 raised power 7 is 128 times this. Okay, so this will come around 6.023. So you can see this is clearly greater than the input voltage. So what we'll do is, in the next clock pulse, we'll discard this one. So what happens is, for the second clock pulse, so what will be the V out at this pulse is, this will be all zeros. 8. So for the second clock pulse, we have 1 assigned to this bit, the second bit, and then all rest of them will be 0, 6, 7, 8. Again, we'll calculate the same thing. So this will be 2 raised power 6. So we'll calculate the V out, that is the VDAC. So this will be 2 raised power 6 times the resolution, which was 0.047. This is 64 times 0.047, which will be 3.011. So now this is less than that of 4.75, that is being given in the question. It's 4.75, right? Yeah. So what we'll do, we'll keep the one as is. So what we can say is, after second clock, we have got 0, 1, 0, 0, 0. Now for the third clock, what we'll do, we'll keep these two same. Now the third one will get assigned here, and rest of them will remain 0. And again we'll calculate the V out or VDAC. So this will be 64 plus 32, that is 96 times the resolution. So this will come out to be 4.572, which is still less than 4.75, that is given in the question. So we'll also keep this one. So after third clock, which is asked in the question, the output will be 0, 1, 1, and then all the zeros. So there will be 5 zeros. So is it understood the problem? Is there any doubt in this? Should I repeat, or is it clear? Okay, so if it is clear, so the correct answer is 0, 1, 1. Yeah, option B is the correct answer. I hope it is clear. Please confirm again if it is clear. Okay, so for the first output, so it is clear, then try to solve this problem now. You can take 5 minutes. This is a similar problem. You just need to check it for this, and this is a 7-bit instead of 8. And the input is given also. Reference is also given. So everything is given. So this is after the start of conversion, and again at the start of fifth. So in the previous question, it was after the end of third clock. So it is at start of fifth. So this will be equivalent to at end of fourth. So you can try it out. You can take 5 minutes and then let me know what is the answer, and then I'll also calculate. Any solution? Or should I wait more? Should I solve? Please confirm. Okay, so take your time. Try to do it quickly. So I'll also start doing now. So we have a 7-bit ADC. Sorry, yeah. So N is 7. So I'll quickly calculate the resolution. So this is V reference where 2 raised power 7 minus 1. So this will be 10 by 7 is 128. Yeah, so this will be 10 by 127, which is 0.0.07887 volts. So again, V reference is given as 10. So I've written 10 here. The input is, sorry, the final output is 8.95 volts. So at 0th clock, we have all the zeros. So we have 7 0, which is less than V in. So we'll keep the bit. So now what happens is at the first clock, we have this as 1 and all of them as 0. So this will be, so we'll calculate the VDAC here. So it will be resolution, which is 0.0787 times this binary number, which is 2, 3, 4, 5, 6. So this is 2 raised power 6, which is 6 is 64. 64 times this is coming out to be 5.03, which is less than 8.95 given in the question. So we'll keep the bit. So this one will remain as is. So now in the second clock pulse, the starting of second is, it will be 1 and this will be 1. Right. Now this will be 64 plus 32, that is 96 times this resolution. This will be 7.559, which is again less than 8.95. So we'll again keep the bit. This one will also remain. So at the starting of third clock pulse, we have this two ones and the third one will come. This will be 92 plus 16, that is 112 times the resolution. So this will be 8.818, which is still less than 8.95 given in the question. So we'll again keep the bit. So at fourth clock, these three ones will remain for the third and fourth will give this one. So this will be VDAC 120. So this was plus 16. So this will be 120 times this 0.0787, which is coming out to be 9.44, which is now greater than 8.95. So we will reset. So this one will get reset to 0 because it is greater. The VDAC is greater than V in. So at the starting of, which is asked in the question, fifth clock pulse, we have this 1110, and at the starting we will do this as 1 and these two will remain 0. So this will be the uh, digital bit at the starting of fifth clock. Is it clear? Okay. So the correct option will be 11101000. So option C is the correct answer. So I'll repeat it quickly. The resolution we calculated, it was 0.0787. So at 0 clock pulse, all the zeros remain, so it will remain the same. Then at the first clock pulse, we calculated this VDAC, which was around 60, which is 64 times this resolution, which was coming. So here VDAC was less than Vin, so we kept the bit. Then again, so we kept and we did the this bit as the one, and again the VDAC was less than Vin, so we again kept the bit. Again, for the third clock pulse, we added this one and still it was less than, so we kept the bit. At the fourth clock pulse, we added this one, but this time the VDAC was greater than Vin, so we reset this bit. So this becomes 11100000, and at the fifth clock pulse, this zero will be now become 1, which I have made it in the green color. And there will be no operation because the question is specified that we need to write the output of the ADC at the start of fifth clock pulse. So that is why it is option C. So now I guess we can move forward now. So these are again theoretical questions. Uh, so again the LSB weight of the weight register. So there are two types of DAC that we have studied. One is the weighted register and one is the R2R ladder. So this works on the principle of KCL and this works on the principle of Thevenin's theorem, or KVL you can also say. So LSB is always given by, as we already know in the resolution also, it is 1 by 2 raised power n minus 1 for any DAC. So it is given for a 4-bit DAC. So we can calculate the LSB, which will be 1 by 2 raised power 4 minus 1, that is 1 by 15. And any weight register is working on the basis of Kirchhoff's current law. So the correct answer is option B here. And similarly, we have already studied this binary ladder, I have already told. So here the resolution is 1 by 2 raised power n, and it is working on Thevenin's theorem. So we'll calculate the LSB, which is 1 by 2 raised power 4. So this will be 1 by okay, it is asking in terms of n only, so it will be 1 by 2 raised power n only, and it works on the basis of Thevenin theorem. So option C is the correct answer. So this is just basic theoretical questions. So now we can do some of the numerical problems for related to these two DACs. So let's go into it. So it is given as R2R ladder network. The input is given as 1011, which is 1 plus 2, 3, 11 in decimal. The reference voltage is also given as 20 volts. We need to find out the output. So we have already done these questions. Maybe you can try it out and let me know the answer. You can take 1 or 2 minutes and let me know the answer. got one answer is 13.75, so we'll check. So it will be nothing. So for R2R, we have just checked the resolution is V reference uh, by 2 raised per n times the V input voltage. So this will be 20 times. This is how many bits? 4 bits. So this will be 16 times V in, which is 11. Mhm. So this will be 55 by 4. This will be 1. This will be 13. Yeah. So 13.75 will be the output, which is the option B. So I hope it is clear. So again, we have a similar question. So we have a 4-bit R2R in which the output voltage is this, the input is this, and we now need to find the reference voltage. So also maybe you can also give the answer in very quickly, or maybe I can calculate it. So V out is 5 volts, V in is 1001, that is 9. So V out is, if I write in binary sense, then this will be uh, V3 by 2 plus, since this is given in binary form, so I'm writing the same. Sorry. This will be 4816, and finally, so it is given as 5, then this is minus, so VREF we need to calculate, then this is 1 by 2 plus 1 by 16, that is a final. So VREF is coming out to be 5 into 16 by 9. So this is 80 by 9, that is 9 8 is 72, 0.89. Or we can directly calculate using that V out is VREF by 2 raised per n, that is 4, that is 16 times V in, that is 9. So from here also you will get 80 by 9, I guess. That will be 8.89. So option B is the correct answer. So I hope it is clear. Shall we proceed?
Yes.
Yeah, so maybe you can try this question out now. I can give you 2-3 minutes. This is again a similar resolution question with the reference to full scale range. So we have covered it in the previous few questions. So just let me know what is the answer, and then I'll solve also the same. You can take 2-3 minutes. Yes, I'll solve the same now. So it is given that the resolution for a DAC, which we already know is VFSR that we have calculated in the previous. It is given that it is approximately equals to 0.4% of VFSR. So basically these two quantities are equal. It is what it is saying. So we need to calculate the number of resolution is given, then it is how many bit converter. So we just need to equate these two equations. So it is saying that VFSR times 2 raised per n minus 1 is equals to 0.4%. So I'll write 100 times VFSR. So VFSR will get cancelled. This will be 2 raised per n minus 1 will be equals to 100 by 0.4, that will be 250, and 2 raised per n will be approximately equals to 251. So we need to find out the closest n now. So for n equals to 6, it will be 64, which is wrong. For n equals to 7, this is 128, which is still lesser. For n equals to 8, this is 256, which is approximately equals to or and also greater than equals to 251. So this can be done using a 8-bit converter. Does it make sense? Is it clear to everyone? So option 3 is the correct answer. Is it okay? Fine. So now we can proceed then. You can try this question out. So again, this is a R2R ladder network only with an additional op-amp. So if you calculate the output by using all the bits, you will get the answer quickly. So just let me know. You can take 2-3 minutes. Am I audible, guys? I think I lost my connection.
Yes, audible.
Fine. So you can type your answers in the chat box if already solved, and then I'll solve. Okay, so we have got different answers. One is A, one is D. So we'll see. So again, what we have is, so we have all the bits given as 1. We have a reference voltage given as 8 volts, and this is again R2R. So it is just an op-amp. So an op-amp, what it is used for amplification. So this will be the total resistance times whatever voltage we are getting is the V out. So there will be an additional negative sign. So I'll just read the V out. So RF is given as, is it given? So RF is R only. So VREF is 8 times minus 1 minus R by R, and this is, all of them are 1, so this will be again 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16, which is 8 minus 8 times 16 by 15, I guess. This is 8 puja, so it will be minus 7.5 volts. So option A is the correct answer. I hope it is clear. So if this is clear, you can try out this question. Again, we have R2 DAC and VREF is given. You need to calculate the resolution. So our what one of the answers is B. So let me solve. This is very easy. So we have 8-bit R2R ladder. So the resolution is straightforward. This VREF by 2 raised per n. So this will give out to be 5 by 8 bits, so 2 raised per 8, so which is 5 by 256, which is 0. 0.019 something. I guess 53 because only option is this. So this will be nothing but 19.53 millivolts, which is option D. So we can move forward now. So again, you can try this out. This is again a simple question with an additional op amp. So now since we have a R by 2 relations, so this is but nothing but a weight DAC register. So you need to apply the logic and let me know what is the answer of V out. So I already have the answer, I guess. Sorry for the delay. So this is again a op amp. So let's calculate this in a very conventional manner. So this is I, let's say. So this is nothing but VA by R, which is 1 kilo, then VB by 2 kilo, then VC by 4 kilo, and then this is VD by 8 kilo. Now the given question we have ABCD as 1010. So this is 1, this is 0, this is 1, this is 0. So what we have is I will be 2.5 times 1k because the voltage has been given for 1, it is equals to 2.5 volts, and this is 2.5 by 4k. So this is nothing but 2.4 times this will be 1 plus 1 by 4, that will be 5 by 4, and this will be 3.125 milliamperes. And finally we need to calculate the V out from the op amp, which is minus minus I times this R, which is given as 1 kilo ohms. So this will be 3 minus 1 point minus 3.125 times, which is R, which is what is R? 1 kilo. The answer will be minus 3.125 volts, which is option C. I hope it is clear.
Yes.
Since we have a negative op-amp, so that is why there is an additional negative sign, so option D will not be the correct answer. So let's move forward. So we have already covered the comparators topic. So quickly let me know in 1 minute what will be the answer to this. Yeah, so for any flash type ADC, for n bit flash type ADC, we need 2 raised per n minus 1 comparators. So it is n is 3, so it will be 2 raised per 3 minus 1, that is 7. So option A is the correct answer. Let's move ahead. So now it is given a sine wave input is given to a 7 bit ADC. So n is 7. We need to find the SNR and also find the worst case SNR. So it is a direct straightforward question. So SNR in dB is calculated by 6.02 n plus 1.76 dB, and the worst case SNR is even a bit lesser. So the worst case SNR is n minus 1 plus 1.76 dB. These are the basic formulas that will give you the answer to this problem. So I'll calculate the SNR first, which is 6.02 times. So what are the bits? 7 bits plus 1.76. This will give you 42.14 plus 1.76, which is 0 789 43.90 dB, and the worst case SNR is basically 43.90 minus 6.02 will be the answer for this. That will be 8 8 and 37, I guess, dB. Worst case SNR will be 43.90 will be SNR, and 37.88 dB will be the worst case SNR, which is option B. Is it clear?
Yes.
So let's move forward. So we have one more type of ADC, which is a ramp type ADC. So it is given, it is a ramp type ADC with all the values of the resistance, capacitance, and the input voltage, which is 3.5 millivolts. So we need to consider the clock frequency is also given. If the ADC generates a digital output in, the clock cycles are 512 clock cycles. We need to find the ramp voltage. So first of all, in any ramp type ADC, the slope determines the final voltage. So the slope of any ramp type ADC, if you have already covered in the theoretical lecture, is VI by RC. So it is, everything is given. It is 3.5 millivolts per R is 2 kilo, and capacitance is 0.5 nano. So this will be minus 6 left in the denominator. So I'll write in microseconds. So this will be 3.5 millivolt per microseconds. I hope the calculations is clear. So once we have this, and the number of cycles are also given, which are 512 clock cycles. So the final voltage we can directly calculate by multiplying both of these. The slope times the number of cycles give you the final ramp voltage. So this will be 3.5 millivolts per microsecond, which will come out to be, um, let me calculate, equal to times 3.5. So this is coming out. So since this is millivolt, I'm converting it in volts. So this will be 1.792 volts. Is there any option like that? Yeah. So option D is the correct answer. So I'm again repeating, for any ramp type voltage, to find out the ramp voltage, first of all, we need to calculate the slope. And if we have the frequency or the number of clock cycles given, we just need to multiply the clock cycles with that slope to get out the final ramp voltage. This microsecond is getting eliminated by the frequency, which is 1 megahertz, which is giving out the time period of 1 microsecond only. That is why we have not considered this microsecond. That is, let's say 1 by f, or f, no, 1 by f, which is again 1 microsecond. Is it clear? You can take 2 minutes to go through this question, and then we'll proceed to the next problem. We shall now proceed to the next problem. The problem says we need to find the output voltage V naught, which is this, in the circuit shown. Okay, so this is the V here in the question, and then all of them are grounded. So we'll again take the conventional way. So we can see clearly here that these two resistance are in series, and then this is 0, so this will be again grounded. So I'm trying to make the circuit out. So this is grounded 2R, and this is grounded 2R. So the combination of them will give a R, because R parallel, sorry, 2R parallel R is nothing but 2R times 2R plus 2R plus 2R, which is nothing but R. So this circuit, the one that I have, so this is nothing but R. So if I try to make a equivalent circuit now, so we can have again, we can again have an R, and again have an R here, then 2R, then again R, then again 2R, and so on. So this will again be 2R within parallel to 2R. So let me try to make again. So this thing will be 2R, and then this thing will be 2R parallel to R, will be R, which is in again in series with R. So this will be 2R. These two things will be 2R. So now I am making the cumulative circuit, because we have a voltage here. We cannot apply the divider rule now. So what I can say is we have a 2R with a ground, We have a 2R with applied voltage V. Then the rest of the circuit remains same, which is this op amp is minus plus. We have a R, and then this is ground, and then we have a V out. So if this is ground, this is also virtually ground. I hope you know this. So let's say there here the voltage is Vx. So we can apply a KCL here quickly. So this will be Vx by 2R for this, plus Vx minus V by 2R for this, and this will be 0. So plus Vx, uh, so this will be plus Vx by 2R. So there was a 2R here. Yeah, so there was a 2R here also, which I have made. Plus Vx by 2R is equals to 0, which will give me 3Vx minus V is equals to 0, and V will be finally 3Vx. Now, since this node is virtually grounded, so we can easily write V out in terms of this also. So what I'll do is the current going through this, let's say it is I, it is nothing but Vx minus 0 by 2R, which is this node only. This is Vx, and the current is Vx minus 0 by 2R. So this is what I have again written. So this will be Vx by 2R. And now we can clearly see here is Vx is nothing but V by 3. So this will be minus Vx because it is internal and the current is going outside. So this will be minus Vx by 2R, which will be minus V by 3 into 2R. That will be minus V by 6. 6R, sorry. Then the final voltage V out is nothing but minus IR. We need to check the resistance if it is R. So it is R only. So you can see here. So V out is minus IR. So I'll just write. Um, sorry, V out minus V out plus IR is equals to 0. So this will give plus IR. Okay. So I we have just calculated this minus V by 6R times R. Final V out will be minus V by 6. So this is nothing but just KCL and KVL. So the correct answer will be option C. Is it clear, or do I need to explain again? Please confirm if it is clear.
Please discuss again.
Okay, sure. So I'm doing the circuit part again. So first of all, these two are in series. So this is 2R parallel to R because both are ground. So this is
No,
getting
actually,
changed.
this portion is clear. This portion clear. Next page.
Yeah, fine. So here what I have done is I have applied a KCL Vx here. So this is Vx by 2R, the first term. Second term is Vx minus voltage, that is V by 2R. Plus the third term is, since this is ground, so this is also virtually ground in an op amp, if you are aware. So this is Vx minus 0 by 2R. So this particular
Okay.
KCL is applied, which gives the final V to be 3Vx. And now the current here is I. So this is ground. So the current will be same as this voltage. So if I apply a KCL here, so this current is equals to Vx minus 0 by 2R, which I have written here.
Okay.
And I have used
So
the value.
here is a 2R. How it is get by 2R?
The resistance here is 2R. Sorry. In the question, the resistance here is given as 2R.
Okay. Okay.
So
Okay.
the current here is equals to this current because it is grounded. So I is nothing but Vx by 2R with a minus sign because I is not going inwards, it is going outwards. So here Vx I applied V by 3, that is we got. So which was the total I is minus V by 6R, and finally
Okay.
here
Understand.
V is
Okay.
nothing
Understand.
but IR, yeah, which will give
Okay.
is.
Understand. Understand. Understand.
So is it clear to everyone?
Yes. Understand.
Yeah, yeah, I got it. So maybe now you can try this question. It is nothing but a 6-bit DAC, which is a ladder DAC. Input is given, for 10 volts is given, so this is nothing but V reference. You need to calculate the output. You can take 1 or 2 minutes max, and then I'll calculate. So just to clarify, this is not a ladder network. There is a typo in the question. This is a weight register type DAC. So don't use the ladder uh, formula. Yes, so I'll solve it. So since this is a weight tag, so V out is nothing but V reference by 2 raised to power n minus 1 times V in, which is 1, 0, 1, 2, 3, 4, 5, 32 plus 8 plus 1, 10 times 41 by, this was a 63. So you can calculate this. It is coming out to be 6.507, which is 6.51 volts. That is option B. Again, the correction was it was a weight register tag, not a ladder network. For ladder network, this would have changed to 2 raised power n instead of 2 raised power n minus 1. So I hope this is clear. So we can quickly move forward now. Again, we have an input wave for a 8-bit DAC. Sorry, ADC. The SNR would be. So we have already done this. This will be 6.02 times 8 plus 1.76. 16, 8, 6 of 14. So it will be 48.9 or 49.92 dB, which is option C. So is there any doubt in today's lecture in any problem? So we can wrap this up because we have covered a lot of problems. So this week it is more about solving problems based on the formulas and the basic knowledge of KCL and KVL. So if you have the knowledge, this topic is very easy and all the questions are direct. One of the most important question or the types of ADC were the SAR ADC question. So please cover that question with a great for the final exams. So this was the question which can be quite confusing because some says at the start, some says at the end, and then we need to see for each and every clock cycle what need to be the BDEC, and then there were basic questions only. So if you have any doubt, you can ask. Otherwise, we can wrap up the session for today, and we'll meet for the last lecture for this course in the next week at the same time. Please let me know if you have any doubt in any question. Okay, fine. Then we can dismiss the lecture for today, and we'll meet. Yeah. Thank you, everyone.